Systems Integration Group, and I want to welcome you to our monthly webinar series and give you a little bit of background on eSig. For those of you not familiar with eSig, we're a membership-based nonprofit organization providing our members with objective information and resources for renewable energy and energy systems integration decisions. We also provide peer-to-peer networking opportunities, information and knowledge sharing, and professional educational experiences. Our most recent activity was our Fall Technical Workshop in Charlotte in October, and our next activity will be the Spring Technical Workshop in Tucson next month, followed by our International ESI Workshop with the Australian Electricity Market Operator in Australia in April. There's still plenty of time to register and make plans to attend. These workshops deal with a full range of issues associated with integrating wind and solar into electric, gas, and thermal systems, and they also deal with the couplings to energy-consuming infrastructures, especially electric transportation, buildings, and industry. Information is available on the website on the upcoming workshop schedule for the year, and all are welcome. eSig is a very unique organization, and I don't think you'll find anything quite like it anywhere else in the world. If you're new to eSig, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, just a few logistical matters before we get started. First of all phones will be muted for the duration of the webinar to avoid unnecessary distractions. So please use the question and answer box on the lower right side of your screen, not the chat box, to submit questions. And we'll try to save 5 or 10 minutes at the end for the Q&A. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the presentation and audio file have been posted. We also plan to provide short responses to unanswered questions after the webinar, so don't be afraid to use the Q&A box. So today our webinar is on the topic of operational considerations for a 100% instantaneous converter-fed power system. Based on registrations, it looks like this is another quite popular topic. The webinar will feature Nick Miller, a recognized leader in the field of renewable energy integration and power system dynamics. Nick recently retired from GE after nearly 40 years of experience in power system engineering and research. He's lectured on wind and solar power integration to governments and institutions in more than 36 countries around the world. He currently provides consulting expertise to a variety of private and public institutions on topics of grid integration of renewable resources. Nick is a man of many talents. He holds 20 U.S. patents for wind, solar, and grid technologies. He's a fellow of the IEEE, a New York licensed professional engineer, and active in CIGRE and IEC. He's authored over 150 technical papers and articles. He's the recipient of a number of power industry awards, including the eSig Excellence Award and the eSig Lifetime Achievement Award. I feel very fortunate to have Nick here with us today, as I do whenever he joins us for an eSig event. On a personal note, instead of telling you that I looked on LinkedIn last night and found out that Nick and I have 170 shared connections, I want to tell you a little story. This goes back at least 10 years to one of the Ackerman wind integration workshops in Europe, when GE went public with its synthetic inertia from wind turbines. I was standing in the back of the room when Nick gave the presentation, full house. You could have heard a pin drop. He gave a really dramatic presentation on the machine capability and why it was significant. It was the buzz all over for the rest of the workshop and really recognized as a groundbreaking piece of work. Nick has had a lot of moments like that, and I'm just glad that I was there to share in one of them and that I can share it with you. I consider Nick a good friend, and I greatly value the contributions that he's made to eSig, to our board, and to the industry during his career. It's a real pleasure working with him. So the webinar today will examine a number of considerations related to operation of power systems with a high share of inverter-based resources, or IBR. The focus will be primarily on technical limitations that are related to stable operation of the grid when most or all of the power is delivered through inverters. The webinar will examine how performance and stability limits with present grid following IBR present themselves, and will go on to discuss how grid forming IBR should be able to relieve some limits, but not others. A few thoughts on where limitations in tools affect our ability to make good planning and operating decisions as we approach 100% IBR will also be offered. So without any further ado, let's go ahead and get started. Nick, I'll turn it over to you.
Well, Charlie, thanks so much for that dramatic introduction. And hi, everybody. I wish I could see your smiling faces out there. But it's a pleasure to have an opportunity to give this talk. And when Charlie suggested this topic, which is an area that I've been spending a great deal of time on, I jumped at the chance. On the other hand, it's also quite a challenge. This is very rich material, and we'll see whether or not I was successful in getting the pieces that you as an audience are most interested in for 45 minutes. So let's go forward. I'll give you a word of context on this talk. It's a mixture of some basics that many of you will be familiar with, although not all, that provide some context. There's a few moments of very quite deep dive that will possibly be baffling to those of you that haven't been immersed. It should be exciting for the few on the call that are immersed. So this is this opening slide is just a quick context, consciousness raising. We're doing a lot of work as an industry, and there's a lot of attention to 100% renewables. Sometimes that's used interchangeably in conversations with 100% converters, and that's understandable, but not quite right in the sense that not all renewables come through converters. Not all converter technologies that are important to the system are renewables as such, but be considered as enablers. So this little, I won't drag you through this slide. You can refer back to it later, but we are focused today on this collection of technologies in the grid that are primarily within the blue circle on the left. Variable renewable resources like wind and solar, batteries, DC, and other kinds of enabling technology. I put all those together in one color. And I include today one synchronous technology, synchronous condensers, as an enabler for converter-based resources. So most of you will recognize this. And I had a slide in there just talking about the language of converters, inverters, rectifiers. It's at the end. You can refer to it later. I think most people in the audience recognize those minor distinctions, and I'm going to be ignoring the distinction between converters and inverters for the rest of the talk. This is another familiar slide. This is also quite important to the overall conversation. The reality of integration of wind and solar and other variable resources is that there are times when there's a great deal of the power coming from these inverter-based resources. So for people that are concerned with policy, you probably, as I said, many of you have seen this slide, maybe often, indeed. This is for a couple of years operation of Public Service of Colorado, running at an annual energy rate of on the order of 25% annual energy. So if you haven't thought about this problem before, you might say, well, annual energy, 25% from wind, that means the other 75% is coming from traditional resources. What's the problem? And of course, the challenge that we are focused on today is that occasionally the majority and approaching 100% of the energy, the power at any given time coming through inverters. I want to drive that home very hard for the balance of the talk today. We are not worrying about 100% inverters for 87, 60 hours a year. We are worried today, and for the balance of this talk, about does the system ever get to 100% inverters or close to it? The other piece of this puzzle that's quite important is that while there are many institutional and economic and practical issues that we wrestle with all the time at ESIG related to variable renewables, wind and solar in particular, the fact that the energy, that the power is going into the grid through inverters really only makes a difference for relatively fast phenomena, stuff that occurs in fractions of seconds to ones, tens of seconds. And beyond that, for the most part, we care that the resource is variable, but we don't really care that it's inverter-based. So the rest of today's talk is in these fast time frames. Not that there aren't other issues, but they aren't particularly predicated on the reality that the power is coming through inverters. That last slide was for all of a chunk of the Western interconnection. That's XL, and that's actually across the XL's footprint. Want to remind everyone that where the renewable resources, where the inverter-based resources are located, is often geographically clumpy, if you will, for lack of a better word, so that parts of the system can go to very high levels of inverter-based resources. This picture on the right is one that many of you have seen. That's a slide from MISO showing a condition where the north part of MISO was at 80% generation from wind. The panhandle of Texas, the northern parts of Brazil, the southwest corner of the Australian interconnection, and other places around the world are today approaching or meeting operation where their chunks of the system are at 100% or approaching 100% inverters.
Hey, Nick, this is Charlie here for just a moment.
Yep.
Fading in and out on my audio, it sounds like you're moving closer to and farther away from the microphone. I don't know if that is the case, but could you try to speak closer to the microphone? Thanks.
I will do so. Thanks, Charlie. Okay, so with that context in mind, we're going to go on to what today's talk, and I'm going to start with some really basic stuff. So I've got this little parenthetical up here. Sorry, this is Engineering 101 for a couple of slides, but I think it's important as I lay out some of the fundamentals of why we need to, some of the challenges that we need to address in 100% converter operation. The first piece of information on this slide is very familiar to most people, and that is that all commercially available wind and solar today not only use inverters, but they use grid following inverters. So that's the challenge that we're facing this as we sit here, and someplace down the road, what's actively being developed today are so-called grid forming inverters, GFI, and we'll get to those after I walk through grid following. So this slide is Power Engineering 101. We've got a three-phase voltage waveform here. This is ABC phase. This is perfectly steady state. Everything is so-called in balance, and we have sinusoids. This is what inverters see, and they have to act on that. Yet most of us work in a phasor world using stability and load flow tools. That green line sees this tripling of sinusoids as a steady state of 1. So nothing would be moving. Almost insulting for me to put this on here, but it's important as we move forward to recognize that the world is this complicated thing, not a solid line. The next piece that is also extremely fundamental and, again, almost insultingly basic is that all grid following devices inject current into the grid. So they use a whole bunch of fancy power electronics and control loops to inject current. The amplitude and angle of the current injection, the orange trace on this, dictates the behavior, the energy transfer out of the resource. So again, everybody knows this stuff. The difference between the angle of the sinusoid, and this is obviously only one phase in blue, and the angle of the current is the power factor angle, and it's really important. So I've pointed that out here. Let's move on though, and think about what it is that the device is trying to accomplish with the current injection. Here, I've decomposed the current, the orange dashed, into two pieces. Again, this is familiar to most of you, but the gray line is the current that is in phase with the voltage. That is the only part of the orange current that transmits power into the grid. The other component, which is 90 degrees out of phase with the gray and orange, transmits reactive power. We care about active power for managing frequency and getting the energy out of the resource. We worry about reactive power for managing voltage. Again, very basic, but we tend to think of P and Q as being separate control objectives. But remember, there's only one current to be injected. So it's the sum and the phasor mathematical sum of those two that's injected to the system. All right, very basic stuff for everybody. So I'm going to walk you through what's happening in the controller here in a conversational fashion. So I've got 5 steps, and I put words in the inverter's mouth. Upstream, the frequency control, the governor function, the synthetic inertia, the power order from the utility, all sorts of upstream controls that we're all familiar with at various levels, give an instruction to the inverter to give me this much power. That's red. There's another controller in parallel with that, particularly in North American applications, that is doing voltage regulation. And it measures voltage error, does lots of things, again, that most of you are familiar with. It issues an instruction that says, give me this much reactive power. That's the purple line. So those things look steady state, and you're used to seeing them in your stability program. The next critical piece here is that the inverter needs to know when to inject the current. And the way it does that is it uses a phase lock loop. That's the blue. The phase lock loop measures the voltage. It's not just the magnitude. And in fact, in this case, the critical element is understanding where that sinusoid is in time, so that it can instruct the active current IP, the reactive current IQ, that was the gray and orange lines, gray and yellow lines, I guess, to be injected at the right magnitude. Those are added together, and finally, the thing that's actually triggering the power electronics results in inject current at this angle. So that's how we get that orange line, is through those 5 steps. Again, very basic stuff, but it's good consciousness raising, because the next thing we have to deal with is the fact that the world isn't in steady state. So in this figure, I have superimposed over my healthy, steady state blue voltage another voltage that's representative of the frequency dropping quite rapidly. Frequency drops, the time between the peaks is extended, and there's a difference. I have left the current stupidly thinking that the voltage is where the blue line is. And you can see here that if the current injection was predicated on the voltage being where the blue curve is, when in fact the voltage is where The gray curve is we don't get the desired active and reactive power injected into the system. Okay? That is the nature of the control problem. Here people are having trouble. I'm trying to hold my head steady. That's not my natural mode of speaking here, but I'll do my best. Okay, so let's move on to that same figure in the fundamental world of when the inverters are big relative to the system. When we as an industry started developing inverters for wind turbines, the presumption was that the grid is big relative to the devices injecting current. Big means that the injection of the current wouldn't move the system. Everything I'm going to talk about in the next several slides is looking at the fact that that isn't really true. So what happens is the system gets progressively weaker, is that the action of injecting current actually causes the voltage to move, which means that the presumption of the control that the voltage is where it was measured or moving in a direction that was where it was anticipating is in fact altered by the act of the control. In the limit, the stability limit, the action of the current injection moves the voltage so much that control does not have the desired outcome, and it can't keep up with the fact that the system is moving. That's how grid following inverters go unstable. It's a very cartoon version of it, but I've avoided throwing lots of equations at you. But you can use the mental imagery that the grid slips out from underneath the current being injected. I've used the banana imagery. So as the system is more movable, that is equivalent to weaker, the action of the control, the action of the current injection perturbs the system more and more, and the control has to be progressively smarter in terms of understanding that impact on the host system in order to stay stable. So controls that aren't designed for a weak grid think that the grid won't move. Controls that are designed for weak grid understand that the grid will move and act accordingly. But in the limit, there's always a stability problem. The other thing is that I generated those nice sine waves with a desktop. It's great to have the assumption of idealness. I went and captured a few sine waves from actual disturbances. These are actual measurements of the current from a wind turbine during a variety of faults. I'm not going to drag you through all the details because it's not important, but as you can see, the waveforms, when the system is perturbed, are not sinusoidal. Each one of the divisions in this slide, in these slides here, are one cycle. So if you look, the first cycle, particularly for some of these, like the second event, are quite hard to understand. The third event's even worse, and it takes a couple of cycles. So what? The so what is that real controls actually need a little time to figure out where the voltage is and make the right action. So it's easy as kind of an armchair engineer to just say, hey, make it faster. Why can't you figure out where the voltage is? But when you start to look at real systems, the problems are actually somewhat daunting, and you can't just keep making it faster and more aggressive. Okay, so I set up a bunch of understanding, I hope, with that hopefully not too painful review of basics, that all point to the notion that you need to know how strong the system is, and that if it's too weak, if it moves too much under the action of the converter, it's going to go unstable. Which brings us to one of the ways that the industry quantifies how weak or strong the system is, and that is short circuit ratio. So short circuit ratio is a very convenient way to talk about how strong the grid is, and I've made as simple a cartoon grid as I can possibly make in the drawing here. Got my converter-based device on the left, stuffing power into a grid that's characterized by its impedance X. Can't make it simpler than that. As X gets bigger, the system gets weaker. As the rating of the device gets bigger, the system gets relatively weaker. Size is everything. A little tiny device can handle a relatively high X. A big device, multiple gigawatts of wind generation, for example, need to have X be smaller. There's a whole bunch of relatively clever analytic tools out there for recognizing that in the real life, it's not just one wind plant or one solar plant, but a collection. So these are weighted or equivalent or composite or effective short circuit ratio. I'm not going to drag you through all that, but I've used this E in front of short circuit ratio to capture the idea that there's a little bit more to this than my simple cartoon. So this is super basic, but quite important. The industry is spending a lot of time and energy, rightly, looking at short circuit ratios as a metric of how close the system is to being able to running out of room, if you will, to accommodate grid following inverters. And so the takeaway box points two things to you. One is that all things being equal, short circuit ratio, as it drops, makes it harder to stay stable. In general, one thing I didn't say on here is that kind of the theoretical limit is the short circuit ratio can't go below 1 with a grid following inverter. Now we're going to dive in. And those of you that have been listening to this and multitasking, but really know this stuff, stop multitasking, because the next two slides are very likely to be new to you and take a lot of concentration. So stop playing games on your phones while you're listening to me. Pay attention to these next two slides. Okay. I have taken my cartoon system where I'm generating power with inverter-based resource on the left, so the cartoon on the left, and pushing all the power through the grid to some infinite place. So that's obviously a simplified cartoon version, but you can imagine that might be the end of the Panhandle in Texas, or out in the hinterlands of the Dakotas of MISO, or Wyoming and Montana pushing power to the east, or massive solar developments in the desert pushing power towards the load centers. Tend to think along the lines of the system looking like what's on the left. But as systems evolve and we move towards 100%, the converter-based resources are actually going to be sometimes remote, sometimes intermingled with where the power is consumed. So on the other end of the spectrum, a bookend, if you will, on the right-hand side, I've drawn the same system in which all the power coming out of the devices is consumed locally. Right? So the megawatts come out and they go into local power. And obviously that's overly simplified, but you get the idea. And there's not a lot of export going on, or none. Those two drawings, using the way short circuit is calculated, are exactly the same. But on the right-hand side, that system is more stable. The angles and the sensitivity to perturbations for the system with the converters on the right-hand side is lower. That is, it has better ability to follow perturbations. It is less likely, less prone to have the voltage move in such a fashion that the phase lock loop can't keep up with it. We aren't talking about this in the industry much. And below in the center here, I made a sketch to capture qualitatively, and I got to emphasize that that this figure is qualitatively, the relationship between exporting power or consuming it locally and the short circuit ratio. So there's three curves here, three dotted green curves that represent going from up, left, and down to the right, progressively weaker grids. The vertical direction is a stability metric, and you can pick a bunch of different stability metrics, but up is good, down is bad. And what you want to learn from this is that all short circuit ratios don't give you the same stability indication. So as some systems migrate forward and get progressively more inverter-based resources consuming the power locally, we're actually going to get a beneficial impact on stability. Right? So this is one aspect where short circuit ratio doesn't tell you the whole story. And quite honestly, the industry hasn't done much to give you quantitative insights into the slope and intersections of those curves that I sketched out here. So researchers on the phone, take note. So now that's one aspect. This next slide is another relatively poorly understood, or at least not widely understood phenomenon. And that is that the power system, you know, we worry about impedance. We think in terms of 60 hertz fundamental frequency, but the power system isn't made of X's. It's made of impedances and capacitance and other things, which means that its impedance changes with frequency. All right, very basic power system engineering. But if we only talk about the X in short circuit ratio, you get on the right-hand side an impedance that changes linearly with frequency. That's the green line on my chart on the right. But the reality, particularly in power systems that are big and long, where just for the sake of discussion, we might be exporting power from a remote, the Dakotas, to load centers in Chicago or something equivalent to that. Those long systems tend to be compensated and they have capacitance. So I've made it simple and equivalent on my left by adding the capacitor bank, and you get the idea, right? As the system gets more complicated, it has natural frequencies, and the solid orange line on the right is more representative of a system that's compensated or has charging, and that is that it's not a straight line. It ends up with a natural frequency. Big stiff systems have a natural frequency that might be 200-300 hertz, but long skinny systems have natural frequencies that start to drop down and get relatively close to 60 hertz. And as you add more compensation, or as the system gets weaker, that natural frequency drops more. So that's what the little sketch of the dotted lines show, okay? These three different systems have exactly the same apparent 60 hertz impedance and therefore have exactly the same short circuit ratio, but the dotted orange line is significantly less stable than the green line. Right? So this is a term that you cannot see with your stability programs. You cannot see with phasor analysis, and yet it's a real consideration for the stability of the converters. Right? One last point is bullet 5. Maybe I should have made that bigger. All right. So conventional static compensation like capacitor banks move that natural frequency around, the way my drawing says. The addition of synchronous condensers looks like making X smaller, not C bigger. Synchronous condensers reduce the slope of the green line, which is beneficial. So all of the things being equal, a unit of reactive power from a condenser is more stabilizing than a unit from a capacitor. There's another whole conversation, which we won't have today, around series compensation, which causes that natural frequency to be less than 60 hertz. We can talk about that on another. All right, so this is kind of new stuff for, I think, the majority on the phone, and it's consciousness raising that short circuit ratio, while it's highly valuable, is not the whole story. Okay, so now we've got these stability models, PSSE, PSLF, various other tools that we all use that are based on phasors that assume that we can actually measure the sinusoids correctly, and we start pushing them to the limits. So here I've listed, and I certainly don't believe this list is exhaustive, but these are some of the classes of failures of the stability model. So you run the stability thing, and all of a sudden it fails to converge, and the run crashes. All right. The reality is that these things are really tough for the algorithms, and the algorithms have a hard time finding solutions. When the simulation crashes, that is an indicator of high stress. It means that the system has got some issues, but it doesn't say it crashed at this point, this is instability. So we're stuck with some imperfect tools, and this is one of the ways it manifests. Another thing that I see regularly now is the simulation starts to thrash itself, and you get very fast frequency in the outputs. Well, be really wary of that, because the reality is that programs like PSSE and all of their kin aren't very meaningful for phenomena that is faster than a couple of ones a hertz. They don't capture the bandwidth of controllers at those higher frequencies, and they don't capture the fact that the system impedance as a function of frequency becomes important. So yes, it's a warning. No, it doesn't tell you. So when you see 10 hertz oscillations in your stability program, you say, ooh, something's wrong, not, oh, the system is unstable at 10 hertz. Probably not. Simulation isn't that meaningful. The last thing that's scary is that stability models can sometimes overlook problems. And we don't see a lot of evidence that that's leading to bad decisions, but that's terrifying for a planner to think that they may have a simulation that says everything is okay, when in fact it's not. And we do see some evidence. Okay. So this slide is just kind of consciousness raising. I won't spend a lot of time on it, but it's nice and fresh off the drawing board. There was a big grid following inverter induced blackout in the UK last August. Huge offshore wind plant with regulators that weren't tuned for weak grid. And these are actual traces from it going unstable. I don't need to spend a lot of time on it other than to tell you, first of all, once the event occurred, they went and looked and they said, oh, we can fix the regulators on the grid following inverters. They did that immediately. It took them a day, and the risk went away for this particular problem. A. B, the phenomenon is about 10 hertz, which means that the simulation, for my earlier point, wouldn't have been so, might not have been terribly meaningful. In any case, they didn't capture this with simulation a priori which is kind of a mistake. So now we get on to a really key point that's going to lead us into grid forming inverters. And that is that grid following inverters actually work really well in that exporting scenario. So these are simulations. Many on your phone have seen me use this slide before. This is a case of a high export from a future Wyoming, in which we've taken the coal plants off, most of the coal plants offline, and pushed progressively more power out of inverter-based wind plants until it breaks. A couple things come out of this that I want to point out here. One is that when the system breaks, it breaks rather rapidly. That's the red trace, so it failed in a handful of cycles. The other thing is that the system didn't give a lot of warning. But the third thing that's really important is that, and I come back to this, this system would have been unstable long before had it been the equivalent with synchronous machines. The system is pushing more power than it could have with standard synchronous machines. So let's go on. So we've got a bunch of tools in our toolbox for pushing stability limits. So the first one I've just talked about, and that is you make more control, the controls on the grid following inverters more robust. So you see, you got a glimpse into how some of that happens with my preceding slide. You can also make X smaller, which is add more transmission, hack more transmission on new lines, hack more transmission on existing rights of way. One of my favorite topics. You can add synchronous condenser, which improve effective short circuit ratio, but introduce possibly some transient stability problems. So we're seeing that two-edged sword manifest itself in different places, including Texas. And then there's different things you can do that aren't wires as such, but enhancement of the grid. So there's a bunch of tools that we have been using as an industry and continue to use to allow progressively higher levels of grid following inverters. But at some point, we need to do something different, and that's where grid forming inverters come in, and they are fundamentally different. Debbie and I have been using this slide for a long time. Grid following inverters need, as you saw earlier, are measuring the voltage and acting to inject current. Grid forming inverters basically create a voltage with the control objective of making the desired amount of power go into the system. It is a fundamentally different beast, even though the devices look similar. So you see me use this slide, many of you, right? So grid forming inverters have been around. That's a picture of me in front of a battery bank with grid forming inverters more than 2 decades ago. But we don't, as an industry, have experience using lots of them mixed. So on this slide, you get, again, my very simple cartoon version of grid forming basics. We now have a device that synthesizes a voltage that I made with this script V. It moves that V around so that the desired power and current goes into the system. It's a lot like a synchronous machine in that regard. It's very similar to a synchronous machine if we ask it to do that, which is to say that the internal voltage, the VI of a synchronous machine, is governed by a whole bunch of physics related to the iron and copper and excitation of the synchronous machine. But we can make VI do anything we want, and I'm going to harp on that for the balance of the next couple slides. We can make VI do anything we want, but it fundamentally alters the behavior here so that the current injected is a consequence of the control action, not the fundamental control action itself. Big difference. So one of the things we need to worry about, and the industry doesn't have complete its head around it, is the fact that grid forming inverters, just like grid following inverters, have limits on the current they can inject. synchronous machines do as well, but the current limits of converters are much harder. I use the word harder in this slide. Harder means if you violate the current limit, you got to fix it really fast. Okay? Synchronous machines with lots of iron and copper are quite tolerant of very high currents. And they have no mechanism directly to control their current. So if you overcurrent a synchronous machine for too long, it will trip, but it doesn't have the mechanism to throttle back the current. Whereas the inverters can take action on VI in such a fashion to bring the current back under control, or they can just say, we ain't doing it. Point here is that this is ground that is going to be important for the industry. How we handle the overcurrents on the grid forming inverters, how much money we throw at it to increase the current carrying capability of the grid forming inverter, and what are the implications of that relative to adding costs and compromising current, and I will use the pejorative, old-fashioned protective practices. So less fault current means that the protective practices may need to evolve or actually be replaced. Spending huge amounts of money to protect decades-old protective practices is something that needs to be challenged, Dick's editorial opinion. Okay, the other piece of this puzzle with grid forming is the inverter itself doesn't create power. The power still needs to come from the resource. It's really easy for you to visualize that for batteries, right? The grid moves, the internal voltage is such that the system wants more power. In this diagram, I've adopted this very familiar NERC drawing. You've seen it many times. This is an old under Oleto drawing that's in the thru. I added to it the synchronous, the inverter-based. That's the purple, so that's my addition. And uncontrolled synchronous inertia jumps its current up, jumps its power up, and it gets sucked out of the grid. That's what the inertia aspect is about. Well, there needs to be a source for the power from the other resources. Easy to see from batteries. In practice, it comes out of the inertia of the wind as well, or it could come out of energy storage on the DC link of the wind's inverter. For PV, there's no inertia, so the only way you can get these very fast responses is if the PV is curtailed. Okay, so it's not just current limits, it's power limits that we have to get right. The other thing consciousness raising is that in this world here, and I'm going to make a circle around it, right? These guys can all be grid forming. I can have perfect control of the voltage of the sending end system. But if I try to push too much power into it, it's going to fail somewhere over here. And that's what the PV curves are about. We are going to see, and I've spent time with many of you on the call, looking at the reality that future modes of failures are going to look more like voltage collapses and transient voltage collapses than traditional loss of synchronism type problems. So that stability limit is still there. Okay, so to wrap up so I can take questions, we are looking down the barrel of a transformation. We've done a spectacularly good job as an industry in making grid following inverters get better and better, more stable, more tolerant of weak grids, more able to respond in a beneficial fashion to grids. But it's taken us 15 years, and there is a limit. We're getting to a point of diminishing returns as the size approaches big or infinity relative to the stiffness of the grids. With inverters, we have the building blocks that allow inverters to look a lot like synchronous machines, but we can do better, and we haven't figured out exactly what better really needs to be. So pounding on the table here to say, we got homework to do. It is clear that we can do better and end up with power systems that make better use of the available infrastructure, particularly the available transmission infrastructure, but we don't have all our pieces together. So I will wrap up with this closing slide on the so-called reality check here. So I've said all these things. We are worried about 100% inverters ever. Ones of minutes of operation on 100% inverters is something that we need to figure out. It's not all the time. There are places that are pushing that very hard. I'm sure some of the people on the phone are from those places. The rest of the industry is well back from that edge, but we need to be learning from those locations. We have experience with grid forming inverters, particularly in batteries. The OEMs are working really hard on it for wind and PV, still early days. Don't make the mistake of saying, oh, just give me a grid forming inverter. It's not a monolithic thing. That's what all these little bullets say underneath. We have an expectation, a reasonable expectation of really being able to do better. We do not have a reasonable expectation of fixing every grid problem with grid forming inverters. And if we don't do it right, we can make things worse. But grid forming inverters aren't axiomatically an improvement over grid following. Let's not make that mistake. We haven't worked our way through all of the unintended consequences. So again, we need to think about it. So good times ahead. We have an opportunity here to continue the transformation of the industry. And with that, I can take questions. And by the way, I'm pretty good about answering emails.
Okay, thank you, Nick. You know, I saw popping up on the screen from time to time questions in the chat box. And I just want to remind you, as I said in the beginning, please put your questions in the question and answer box, not in the chat box. We can't deal with them in the chat box. So I'm going to go over to the question and answer box back to the beginning. Steve Boyning had a couple of questions about latency. What is the latency of today's controllers and keeping up with the system signal? And then, does inverter design create the ability to remove harmful harmonics from the grid? Could SSR frequency components be actively damped using inverters with lower latency? I'll take a crack at that, Nick.
All right, so Boyning takes advantage of being first in the queue with 3 questions. All right, so there's 2 questions here. There's the latency is often associated with the fact that you've got, for example, a farm or a farm of turbines, wind turbines or PV, and there's time between when the master controller at the point of interconnection talks with the individual devices. That's a tricky thing to get rid of, and you know, numbers measured in the many tens to hundreds of milliseconds for farm latency are pretty common. The other aspect that to some extent drives the kinds of stability things that I'm most worried about in this lecture are right at the inverter. So it's not so much latency there as ability of the phase lock loop to keep track of where it is and when the world is moving rapidly, and to understand things like phase jump as opposed to continuous motion. So yeah, latency is an issue, but it's just a piece of it. Damping of subsynchronous resonance, there's kind of 2 pieces of that. One is to make the turbines themselves immune to sub-SSR. The industry has made great progress on that, and the OEMs are, at least the big OEMs kind of have a pretty good answer to that. Using them to damp other SSR is a second frontier. The short answer is yes, it's possible. The long answer is location, location, location. You need to have modal controllability, and it's not a given that your resources are in the right place to get the right leverage on the load chain. And I only got 2 of the questions. What was the other one?
It was the one on subsynchronous resonance, SSR.
I did that one.
Oh, okay. Well, we'll
Let's go.
move on to the other. I think we probably spent enough time on that.
All right.
Question from Deepak. On the slide showing the effective short circuit ratio with all the power being consumed locally, how would the analysis change if the value of X is calculated after taking into consideration the local load? 7X, which takes into consideration the local load.
Yeah, certainly you get a different, Deepak, you get a different answer, and you have to be a little careful about how you treat that local load. So if you just turn it into an R and an X, you get what I believe the current work suggests is an undue amount of damping. But the point is, yeah, so that is directionally correct. Whether the tricks used for including that are sufficient to reflect the effect, I'm not ready to answer.
Okay, more work to be done. A question here. If you limit the current of the grid forming inverter during faults, do you believe it will still work as grid forming?
Well, you know, anytime you're banging against the current limit and driving that hard, then your control objective is compromised. So I gotta waffle on that a little bit. When it's hard against limits, it isn't the same control as when it's not hard against limits. Is that grid forming? And what exactly is being formed during a violent event, even by a synchronous device, is open to some discussion. One of the issues is, you know, how does it behave during the fault? A related issue, but not identical, is how quickly can it recover from the fault and figure out where it is. So one of the nice things about, you know, the beneficial things about grid forming is the fact that it is kind of passively, I hate to use that word, you know, creating voltage. So the expectation is that when the fault is removed, just as when there's other kinds of stepwise disturbances, its innate response is beneficial. So I think the short answer is yes, with an asterisk. Not quite the same.
Here's one to give you a chance to discuss a little bit of balancing considerations. For a 100% inverter-based power system during a short circuit fault, if all inverters limit their current to 1.5 per unit, this will cause a system-wide low voltage and affect many customers. Should IBRs have higher current ratings?
Yeah, so there's two parts of that, and certainly the fact that the reactive current delivered during the disturbance is, in general, at least economically, is or whatever, we can have this discussion, is lower, means that the area affected by the disturbance is wider and affects more customers. Whether or not that has reliability or economic consequences is, I think, a question that needs to be asked. The fact that more people feel the disturbance isn't, you know, do we really care? Maybe we do. The ability of the system to deliver current relative to protection becomes important. So, and I made some comments about that. That's a long answer. Yeah, but the final thing is everything, right? When we get to 100% inverter, so my little cartoon version here, you know, with a single device, when the single device slams into currents, that's it, right? When the last converter runs out of control range and bangs into current ratings, it's done. System is not stable and it fails. So in an interconnected system with a multiplicity of size and physical location inverters, the devices that are nearest to the disturbance might saturate, but you can't have all of them saturate or you're dead. So that's one of these questions that we need to understand institutionally, is how far out does that ring of saturation go? That's not quite the question you asked, but it's part and parcel of it. And we got some.
Okay. Yeah, we're going to have to wrap it up, Nick. We're at the top of the hour now. I didn't get to all the questions, but we're going to ask Nick if he would take a crack at providing short answers, and that'll be available when we send out the email with the audio and the slides. We appreciate your engagement, everyone. Look forward to seeing you at our next webinar, which is on Tuesday, March 31st at 11 a.m. Eastern, 5 p.m. Central Europe. The webinar will feature Dr. Linda Steg, a professor of environmental psychology at Groningen University in the Netherlands. It'll examine a number of considerations from the social sciences related to the critical role that customers and their preferences play in the success of integrated energy systems. Still have to deal with those pesky customers. It's a not so well understood topic, and I think it promises to be a very educational one for all of us, so I hope you'll be able to join us once again. Further information on all the webinars and meetings can be found on the website at www.ecig.energy under events and our newsletters and informational emails. Nick, I want to thank you again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you next month with Linda Steg on consumer preferences and energy systems integration, or at the Spring Technical Workshop in Tucson. In the meantime, take care, everyone, and thanks again for your participation.
Thanks, everybody, for